Hello everyone, I'm Shu-Hao. Today I'm going to talk about detection of camera model inconsistency and the existence of optical image stabilization system. Visual SLAM is the fundamental for robot localization and 3D reconstruction in computer vision. As mobile devices are common and the techniques such as augmented reality advance, Visual SLAM package is more accessible and easier applied in our daily life. For example, Lego construction auxiliary app using AR. However, it requires precise camera model to enable accurate environment mapping, which is often compromising. It can be easily violated as the camera projection model change, which can be introduced from device aging or optical image stabilization. Optical image stabilization is also called OIS and has been widely adapted in camera, especially smartphone these days. It is a mechanism to improve image quality by moving optical lens to compensate for the image blurring caused by involuntary motion such as hand jittering. In brief, OIS detects the involuntary motion by the device like gyroscope, and then it shifts or rotates the lens in the opposite direction to cancel and reduce the blurring. So why OIS affect the camera projection model? Here we use an illustration to show OIS working principle. Once the hand jittering happens, the corresponding image point is shifted on the image plane. With OIS, we can shift back the image point and reduce the image blurring. We can see that once OIS is activated, the optical path is changed and the geometric relationship between the physical lens and the image sensor is no longer the same. And those facts can lead to a different camera projection model since the optical path is possibly no longer traveling in the same way. Currently, most devices ignore OIS existence by using a lower resolution image when applying AR API, which limit the AR mapping accuracy. The purpose of our work is to pave the way to the development of an adaptive camera model for OIS-enabled devices, and also to provide understanding for camera model accuracy for future high-resolution AR applications. Our approach is a two-step algorithm to detect model consistency and the existence of OIS systems, which is composed by two statistic hypothesis testing. We use checkable grid point as input. Our first hypothesis testing is to verify if the collinearity property is preserved for the collinear grid under the existing camera distortion removal process. Then we design another hypothesis testing to verify if the camera intrinsic metrics match the image point. To understand how OIS impact the image processing, let's review recent OIS development and the projected geometry. OIS has been widely adapted in the camera, especially for smartphones, in order to get a better image quality under hand jittering effect. We can classify OIS based on their actuator type. Common actuator including voice coil motor, liquid lens, and piezoelectric motor. Among them, voice coil motor has become the mainstream actuator for smartphone cameras due to its compact size, simple structure, and high efficiency and accuracy. OIS compensates for the camera movement by altering the optical path after detecting the vibration. The issue of variable camera intrinsic parameter for camera with OIS mechanism has not gained much attention, even though camera with OIS has become more and more common. As an early work, CIPV mobile includes the camera intrinsic parameter into the state variable to achieve robust pose estimation. However, CIPV mobile assume that servo actuator measurement are known, which may not be reliable in mobile phone camera. Our work does not assume no actuator measurement and only rely on image taken by the camera. Projected geometry in computer vision describes the relation between 3D points in the word coordinate system and the image 2D point. It is the foundation of vision-based robotic localization and 3D reconstruction. Camera perspective projection model, also known as pinhole model, is the most widely adopted geometric model, since it employs a robust linear model to describe the perspective mapping from 3D points to 2D image points. The model parameter can be easily interpreted by using the camera intrinsic, including the focal length, principal point, and the extrinsic parameters. Our work also assumes that our camera model is using pinhole model. The projected geometry model in computer vision often assumes that there's no nonlinear distortion in the image. Namely, the points on the straight line must be imaged as points on the straight line. The collinearity recovery usually can be achieved through camera calibration by removing the lens distortion. Besides, common lens distortion can be classified into radial, tangential, and thin prism distortion. Our work can detect if the lens distortion removal is complete to ensure that the underlying assumption in applying geometric model is still valid. Our problem definition is defined as follows. We take the prior calibration matrix and the checkerboard correspondence as input. We first determine if the lens distortion removal consistency exists in the rectified image. If the lens distortion removal consistency exists, then we determine if the camera intrinsic parameter consistency exists in the rectified image. Here we show our system diagram. Our algorithm consists of two main blocks: lens distortion removal consistency test and the camera intrinsic parameter consistency test. If the inconsistency of either the lens distortion removal or the camera intrinsic parameter exists in the rectified image, we then determine that OIS has been actuated during the image capturing, since the OIS is the only factor able to change the geometric relationship between the lens and the image sensor. Now let's move on to the detail of each block. We want to verify if the lens distortion is removed completely from the rectified image. It is crucial since projected geometry is defined by assuming that the conservancy of collinearity in the projection. It also means that the image has no lens distortion. The projected geometry model estimation can be corrupt and fail if the lens distortion removal is inconsistent. To check the collinearity, we use the lines from the 2D grid, which is formed by the checkerboard point. We first estimate the 2D grid line. Then we design a hypothesis testing for collinearity. The collinearity of points from the 2D grid is measured by the average distance between the point to the estimate line. When the collinearity is preserved, the average distance between the point and the estimate line must be small. We consider the collinearity is preserved by rejecting the new hypothesis. Otherwise, we consider that the lens distortion removal is not complete. Next, we want to examine if the prior camera intrinsic parameter is consistent with the rectified image. We began with the camera pose estimation by using the standard maximum likelihood estimation. After we obtain a camera pose, we want to verify if the camera intrinsic parameter consistency exists or not. We use the reprojection error of the checkerboard point to measure the camera intrinsic parameter consistency. For each checkerboard point and its reprojected point, we design a hypothesis testing to check if they match with the camera intrinsic parameters. We consider that the point and its reprojected point agree with the camera intrinsic matrix by rejecting the null hypothesis. The overall camera intrinsic parameter consistency is evaluated by checking the ratio of the checkerboard point and its reprojected point, which agree with the prior camera intrinsic matrix. If the ratio is higher than the threshold, we consider that the camera intrinsic parameter consistency exists in the rectified image. In the experimental part, we evaluate the camera model consistency detection accuracy. We use the standard classification results and measure the detection accuracy by precision, recall, and true negative rate. We first want to verify if our lens distortion removal consistency test is able to detect the incomplete lens distortion removal from the image. In this task, we classify the image into two categories. DC dataset represent the image without the complete lens distortion removal, and the non-DC dataset represent the image with complete lens distortion removal. In this test, the precision, recall, and the true negative rate all can achieve 100%, which means that our lens distortion removal consistency test can successfully detect if the collinearity of image is maintained. We are also interested in whether our method is able to detect OIS using the two-step camera model consistency test. In this test, we also classify the image into two categories by considering if the OIS is actuating or not. To avoid the OIS is actuated, we fix our camera with the stationary post on the mounted stand. Otherwise, we handhold the camera to that OIS can be actuating during the image capturing. The experimental result shows that we can achieve 100% in both precision and the true negative rate. And it means that our OIS detection method only classifies the image from OIS data set into OIS set, and it doesn't misidentify the image from the non-OIS data set into the OIS set. Recall can achieve about 85.4%, and it shows that our OIS detection method has been very effective. 85.4% recall is a not negligible rate, and it means that we are highly likely to face the image with inconsistent camera model when the camera is hand-holded, which is common in such an AR application. Besides, 85.4% recall also means that the false negative number is not equal to 0, and it's 23 in our case. The non-zero number means that the image with OIS actuating still sometimes can be consistent with the prior camera model. This is expected because OIS effect may or may not introduce a noticeable change in the camera model. We are also interested in whether the camera post accuracy is different between the OIS set and non-OIS set according to our OIS detection result. We want to verify if the inconsistency of the camera intrinsic parameter results from OIS. Therefore, we include the camera intrinsic matrix into the parameter vector of MLE for the image in the OIS set, which is represented by OIS plus K star set. The evaluation metric here is the standard reprojection error. The results show that there exists a significant difference of average reprojection error between the non-OIS set and the OIS set, and confirm that the camera intrinsic parameter vary when the OIS is actuating. Besides, the average reprojection error reduced from 0.45 to 0.23 after including the camera intrinsic matrix into MLE, which confirmed that the camera model inconsistency introduced by OIS is not negligible. To summarize the contribution of our work, we report the algorithm in detecting the camera model consistency and the existence of OIS system. One statistic hypothesis testing in detecting the distortion coefficient inconsistency, and another statistic hypothesis testing in detecting the intrinsic metric inconsistency. The experimental result shows that we are successfully detect the model inconsistency and the existence of OIS. Our result shows that we can achieve 85.4% recall and 100% precision. Our future work including analysis the relationship between the camera model and the OIS system. We also want to develop a camera model tracking algorithm to further improve the robust AR application. Thank you for listening.